Okay. Hey. So I've always wanted to explain computers in a way that people could make some sense of them in a very natural sense without having to understand a lot of math and take logic classes and all this stuff. And I've been thinking about this since I was for over 20 years. And I'm hoping that I've finally figured out a way to do it. This is just a cute little play thing here. It has nothing to do with my subject, but I want to show it off a little bit before we start. So what this is it's just Squeak. If you've never used Squeak, Squeak is the program that's used on one laptop per child program. It makes a nice, easy programming environment, although the fact is I don't have a lot of training in it, so it's been a long time for me to figure things out. And I also had this old thing that I was interested in. I used to call it the BIRD program. It's supposed to be an emergent behavior demonstration where you give some objects some really simple behaviors, and as a collective they exhibit a slightly more complex behavior. So what I did was I made these little blocks, nothing too fancy, and each of them has a little script attached to it. And if you run the script, what happens is the big blue blocks move towards the green block, and then they sort of circle around the green block, which is cute. And then if you move the green block, the blue block moves towards the green block. Very simple, right? And I can lead this thing around all day, and it will always follow me. And when it gets next to me, it'll just circle around in the area. So that's cute. Well, that's sort of the highest end of applications involving computers. That doesn't have any low-level stuff in it. It's very easy to see what's happening. Wherever I leave the green box, the blue box follows me. Now, explaining how that works is a totally different story in a technical sense. So I'm not going to try to do that, but I just wanted to show you some of the cute little things that you can do with all this fancy stuff. Now, what I really want to do is go backwards from this, go sort of all the way back to the point where most people, if you try to explain computers to most people, they sort of get this, they'll occasionally get this sort of glazed over look where they vaguely understand you, not really entirely. And usually the point where that happens is when you start saying things are zeros and ones. I think what's confusing about that is when somebody looks at a computer screen with a blue block on it, with a black line around it that I can move around as if it were a real block, and then I turn on the script and that block starts moving, and I move something else and it seems to follow it. It's all zeros and ones. It doesn't really cut it. It doesn't explain why this is doing that to a normal person who has experience with normal everyday things. So rather than try to explain the entire behavior of this system, what I prefer to do is to sort of work my way back to the simpler questions of, for instance, how do we know, how does the computer know that at this position on the screen to display a dot that is green or other color green? And I say dot because the computer screen is made up of tiny, tiny, tiny little dots that you can't see. And the way it displays this stuff is it just makes that light coming out of there, out of the screen at that point, it makes that light the color green, and it makes the light here on the line the color black, and it makes the light in this background area the color beige or some weird variation of beige in the different areas where it's supposed to look like paper and shadows, or it makes it look like turquoise, whatever that color is. And I think that's where people kind of tend to shut off their listening apparatus when you get to trying to explain, well, that green is just a number. Because they're looking at the screen, it's not a number, it's the color green. So why is that? And the answer is a long and painful one to get to. But if you imagine the screen as just a series of dots, and I'm going to make a series of dots here, and you imagine each one of these maybe beige or maybe green or maybe blue, and if you had these 5 blue and these 5 blue and these 5 blue, you can see how this area being blue might make that look like a block that's blue. In fact, you can do something called ASCII art, where you type the same letter in the same position. You can make shapes. I'm not particularly good at ASCII art, so I'm just going to make a block. And there's your, they call it ASCII art because the code for the letters is called ASCII. And that's another thing. People, well, why is it called ASCII? What does that mean? And that's actually a really good place to go to. So we've gone from blue blocks, and we'll sort of ignore the fact we're going to avoid that question of why is it blue. And we're going to move over here and say, well, why? How does the computer know to stick a B there? Which is a similar, although not entirely exactly the same question. And if you were to look at the internal representation, there's a list of numbers that represent this screen. And each one of these characters has a number associated with it. And I know that that doesn't explain things very well, but just keep that in the back of your mind, that there's somewhere in the computer where this actually looks like, I don't know what the number is for dots, I'm just going to make it up. I don't know what any of the ASCII stuff is, so I'm just going to make it all up. So there's a dot, there's a dot, there's a dot, there's a dot, 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 dot. And then we'll make a B, which would represent, you see the dots, 1, 2, 3, 4, 5 dots. So let's make 5 dots. And then we start with B's. So there's the first, the 66 is the first B. And we have 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. That represents those B's, and then we'll make a couple more dots to represent these dots here. I'm not going to go crazy. And then we do the same thing down here. There you go. We're slowly working our way back in representation of this idea. We started with blue rectangles. That move we got, now we've moved over to representing those rectangles. The color inside the rectangle, we're representing it as a bee instead, as a group of bees. And this doesn't move, this just sits there. The movement behavior has been, I've sort of taken it away. And I'm just representing in a much more simple form the fact that there's colors of one kind, and then there's a big area of colors of another kind, and then there's more of the beige stuff behind it. And all the complicated stuff has been taken away, and now we're just worried about how do we know that there's a block of blue color there. So there's a block of bees, which could instead be something of blue color if we wanted to. And now I went backwards again, and here's a block of numbers representing this area of the screen. Okay, I don't want to spend too much time on that. It's a video, you can rewind it if you didn't get that. So, like I said, these numbers here came from something called an ASCII chart. That's what it's. That's the word ASCII, although it's not really a word; it's an acronym. You can look that up. Another question is, okay, you've written a number, but where in the computer is that number? And I think that's what people don't get. How does this blue color come from a number somewhere in your hardware? Somewhere there's a box. You know, I'm sitting next to my computer. It's got a motherboard and a processor chip and some memory and a video card. And somewhere in those pieces of hardware is the number 66 that represents, and then somehow it gets represented into blue. So how do we do that? Well, inside the memory of the video card, so there's a little chip that has spaces to write whatever numbers you want. And my screen has a dot for every single little bit of color. And I don't know my resolution, but let's say that it's probably reasonable to say that going across all the way from left to right, if these dots are so small you can barely see them, it's reasonable to say there's 1,000 and something dots. So then we'll say there's 800 dots going from top to bottom. And so if we multiply that, we get 800,000 dots in these little areas on the screen. Well, somewhere in the video card, we've got 800,000 places for a number representing each dot. Which is really true. There's a little circuit that has it's called memory. This would be probably video memory, and there's 800,000 little, what we call bytes, or 800,000 places to put the number 66 or the number 23. Now, how do you store 66 in electronic form? Well, then you're starting to get into what I really wanted to get down to, which is representation. So take the number 23. That's equal to 2 times 10 plus 3 times 1. I think is pretty clear. But you could also say that it's 2 times 10 raised to the first power plus 2 times 10 raised to the 0 power. Now, if you're not a math whiz, it's not a big deal. Basically, we call this in like grammar school, we call this the ones place. So the 3 is in the ones place, and the 2 is in the tens place. So the ones place is you take what they call the base, the number system that we're in. We're in a base 10 number system because we count from 0 to 9. That's 10 numbers. And then for the number 10, we have to put a 1. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then in order to get the next number, we have to make a tens place and then a 0 in the ones place. And then a 1 in the ones place and a 1 in the tens place and a 1 in the ones place makes 11. And a 1 in the tens place and a 2 in the ones place makes 12. And what that means is we're multiplying by 10. This number here gets multiplied by 10. We got all the way up to 99. Then we have to make another place called the 100th place and put a 1 in that. And the 9s get flipped back to 0. So what we've done is we've added 1 to 99. This 9 has become a 10. Well, we can't have a 10 in just one digit. So we make it a 0 and we add a 1 to this place. We add 1 to this 9, that makes it a 10, so it's a 1, 0, but we only have one spot, so we can't put 1, 0. So we get out here and we put the 1 out here, and both of these are flipped over to 0. And you could think of it in terms of a clock as well. You picture a clock with 10 numbers on it, and the little hand, you picture the clock. Let's use this one and rotate it. You can picture the clock rotating. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that goes back to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So it always comes back to that 12 and 12 followed by 1. Well, with the tens numbering system, which is it's called decimal, and it's our normal, the one that we're used to, you do the same thing. Only instead of 12, you go by 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you want to go with zeros, you want to talk about the zeros, you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But you can also say 0 there. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And so as you make bigger and bigger numbers in this system, the way that we do that is we make more and more places where we put numbers, and I'll use these boxes to demonstrate the idea. So for right now, these boxes all basically, this green arrow will be the pointer. These boxes all point to what we'll call 0, which is make it the top of the box. We don't have a number there. Maybe I'll just stick a number. Just put a number at the top of those. So we'll say that's just 0. All right, good. So now this box points at 0. And we'll just make copies of that. Okay, so then our boxes point at 0. If this box was in the middle of a clock, it might have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it goes back to 0. So we'll treat this as a regular counting numbers. We're going to count from 0 to 9 with this block. So we'll start at 0, and we'll rotate this to the number 1. And then we rotate it to the number 2. And so on and so forth. And I could write a little script, I'm sure, to do this. It goes 1, 2, 3, 4, 5, 6, 7, 8. And now it's pointing at 9. So here's me going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And my next thing I do is I do a 10. I make a 10. Because that's the next number in the sequence. For those of you who don't know how to count to 10 yet, I apologize. So to make a 10, I can't make a 10 in here because I'm only allowed to do one. I'm only allowed to go from the 9 to the next number on the clock, which in this case is actually 0. So the 9 can only go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Well, now I have, instead of 10, I have 0. So that's not helpful. So what I want to do is I want to make this, I want to represent the number 10. I put a 1 in this position. And this is times 10 raised to the 1. And we'll just mark this as times 10 raised to the 0. Hi, baby. Awful. But I'll beat it. So since this is on 1, we're going to rotate that. And you can picture this goes around again. We get to 9 again. And then we need to rotate this one more. And this can only go to 0. So this goes back to 0. But then we have to represent that we have 20. So now this points at 2. And this number is now 2. So now we have 2 times 10 to the 1 plus 0 times 10 to the 0 equals 20. Okay, that was kind of a long sidecar. But the point of it is that the way you make a number out of digits is you have single digits. You have a single digit place, and then you multiply it by, we call this the base. In this case, 10 is the base. And this is the place. So the 3 is in the, we call it the ones place. You can also call it the 0th place in the number. It's the place where we put the single, the ones. The 10's place is where the 2 is. You can also call it the 1th place, or the 1 power of the base. Now the reason to go into all that nonsense is that 10, the base, can be changed. You can pick a different base. So say, for instance, I didn't want to use digits 0 through 9. Instead, I wanted to use another base. So I said, I want to use digits 0 through 7. Okay, so I can count 0, 1, 2, 3, 4, 5, 6, 7. I can't use the number 8 because I only allowed myself digits 0 through 7. I just made that up. I just decided. So how would I make an 8? Not by writing an 8, because I don't know what an 8 is. I don't have a box of 8s. Like, think of Scrabble letters, and you only have 0 through 7. How do I say 8? Could be a ton of ways. The way that I choose is to say 8 equals the base times, 8 equals some digit times some base raised to some position plus another digit times some base raised to the position. Well, what's the position? Already used up the 0th position, or we'll call it the ones place again. The ones place is only allowed to go to 7. So we'll call it the ones place or 0th position. My highest digit in the 0th position is a 7. And in the case of the tens numbering system, what I would do when I ran out of digits in this position is I would put a 1 in the next position out. So let's try that. And 8 in decimal equals 0 in the ones position plus a 1 in the next position out. Okay, so if we're saying that's 8, then that means that 8 equals digit 1 times some base raised to the position. The position is, remember, it was 0th place, 1th place. So the position is the 1th place. I'm going to add to that the digit 0 times some base. It'll be the same base raised to the position, in this case, position 0. A little typo there. I made a typo. I had and instead of caret. Caret means raised to the. So somehow that is equal to 8. All right, well, 1 times, we'll call the base, we'll just call it x. Raised to the 1 is x to the 1 equals 1 times x. X to the 1 equals x. So 1 times x to the 1 also equals x. That's easy. So that's my first 1 times base to the 1. Call the base x. That's probably confusing. We'll just leave it as base. So 8 is equal to some base to the first power plus 0 times base to 0. Well, 0 times anything, base could be 10 million. This will always be 0. So I can just ignore this part of the term. And I can say 8 equals 1 times base raised to 1. Well, anything raised to the 1 equals itself. So that is equal to 1 times base. And if you're not familiar with raising things to powers, it's just multiplying things by themselves. 0 and 1 are weird cases. They're defined as anything to the power of 0 is just equal to the number 1. And anything to the power of 1 is just equal to itself. So 1 to the 1 equals 1, 2 to the 1 equals 2, 3 to the 1 equals 3. And spacing is not relevant. It looks like I'm trying to say something with spacing. 3. And it keeps going forever. So anything to the 1 is the same as the thing, as that thing itself. So if 8 equals 1 times base to 1 and base to 1 equals base, then 8 equals 1 times base. Well, that's easy. Any 1 times anything is just itself again. So I can just get rid of the 1 and say 8 equals base. All right, so now we know what base we're in. This is called octal counting. So it's base 8. It has digits 0 through 7. And in order to make an 8, you make what looks like to us a 10. And this is going to be typical of numbering systems. Let's make another numbering system. We'll just choose randomly that it's going to be base 6. So we're going to have 6. We're going to have digits always start at 0. And we're going to have digits 0 through 5. So the digits always go up to 1 less than the base. Now I want to count. I go 0, 1, 2, 3, 4, 5. Now I can't make a 6 because I don't know what a 6 is. So I have to make a 1 in the 6's position and a 0 in the 1's position. And then a 1 in the 6's position and a 1 in the 1's position. That's a 7. I'll just put their decimal equivalents here for reference. And I can do 1, 2, and that equals 8 decimal. And so on and so forth until, say I have 1, 1, 1. Well, that's, what is that? That's 1 times 6 to the 2 plus 1 times 6 to the 1 plus 1 times 6 to 0. That equals 6 squared plus 6 to the 1 plus 6 to the 0. And writing that out in decimal, we get 1 times 6 to the 1 to the 2. 6 times 6 is 36. 1 times 36, that's 1 times 6 to the 2. Now 1 times 6 to the 1, add that. What is that? Well, 6 to the 1 is 6, and times 1 is 1. So there's 6 again. And then the last term is 1 times 6 to the 0, and that's easily, you add that in, and that's easy. 6 to the 0 is 1, so you actually just end up with the number 1. So you have 1 in the 1's place, 1 in the 6's place, and now it's a 1 in the 36's place. Why base 6? Doesn't matter. You can do this with any number, and then you can translate it to decimal using this little trick. The place times the power raised, the digit times the base raised to the power. That's how you do it. All right, so all of that was just to kind of get your mind around the idea that you can have numbering systems that aren't the ones that you're used to. And what happens is many, many years ago, people were trying to figure out, how do we make an electronic computer which has voltages represent usable information? And that's really the ultimate, the founding and important question with computers, is how do you make them represent something that's useful to us? Well, how do I get a piece of paper? One way to approach it is to say, how do I get a piece of paper to represent something that's useful to me? Like, for instance, if we take the program Paintbrush that does a nice job of drawing lines, I can make all kinds of squiggles and nonsense on here. And isn't that wonderful? But none of that makes a bit of sense to you. However, if I'm living in a place with the English alphabet, I can make this shape, and you will know that what I mean is the letter A. I can also make this shape, which is completely different from that, but you know that those two letters represent the same thing. And if your name, for instance, is Adam, you know that the first letter and the third letter in Adam are A's. And the same with the D. I made some weird funny shape with a thing like that, and that means D to you. And I made this M like this, a little tail on it, and that means the letter M. And so you look at these shapes, and you know that it represents the sound ah, or ah, or or whatever. And you know how to make your mouth make that sound. So you've, a pair of Rolling Stones lips. Ah. So you practice for a long time when you're a little kid making these letters. And then you practice putting them together into words in English. And then you spend a long time going, Adam. Sound that out. Bite. Why doesn't that E make a sound? How does that? How do we know that that's a long I sound? All these little things. You spend a ton of time learning that stuff, and this is what's called representation. Because by itself, a shape doesn't mean anything, but you and I both know that this shape means @ sign, and @ has all kinds of funny meanings in our language, which you happen to learn about as a little kid. Here's another symbol that has tons of meaning. And yet, if we were to make just a weird lines that's very similar, that doesn't mean anything to us. And it's not even that different. I mean, it's basically sort of mirror imaged it and made it pointy. Okay. So the idea is that we can choose whatever representations we like for things. So we chose this one for money and didn't choose this one, as far as I know, unless that means something in another language. We chose that this I in between the B and the T with an E on the end of it makes an I sound and not an I sound. And then we decided that that I would make a short I sound. I think that's how you represent that. Width. Okay. So now we've got representations. We've got the fact that we can choose representations, and we have the fact that we can do things, we can choose a representation of numbers of our choice. What that rolls into is that we can choose a new base. And we're going to choose one that's easy for computers to represent. We're going to choose a base 2 numbering system. And the reason computers can represent this easily is you can represent this as either on or off. And you can, on or off isn't really a computer hardware thing. These are represented by voltages in the hardware. And we just interpret a certain voltage region as a 0 or a 1. And a 0 is off and a 1 is on, and we've just decided that. It could have been the other way around. But the one we chose was off, on equals 0, 1. Okay? 0 equals off, 1 equals on. We can just choose some random voltage. Let's say on equals 1.5 volts. That's a AA battery. And 1 equals 9 volts. That's a 9 volt battery. So whenever you want to hook up, make something that's the number 1, you can just take a voltmeter to a 9 volt battery. There's a 9 volt battery with a couple of wires coming out of it. And you hook that up to a voltmeter. And there's a little needle. And there's a 9. So you hook that voltmeter up to positive 9 volts, and you get a 9. That doesn't look very much like a 9, but you get the idea. So we'll call that a 1. And we just chose that. We just randomly decided that a 9 volt battery equals a 1, and a AA battery. Let's make a AA battery. Let me erase some of this garbage. So now I take a AA battery. My drawing is atrocious, but atrocious. And there's our AA battery. And we take a wire and hook that up from there, and there's a wire coming from the bottom. And we connect those into a voltmeter, and there's a little needle at the end of the needle, and you read the number. I'll say 3. It wasn't 1. It was 1.5, but I'll just call it 3. So there's a 3 volt, and there's your 9 volt, and we just decided that 1 then 3 volt is 0, and the 9 volt is a 1. Anything in between, we don't deal with. We only deal with 3 volts and 9 volts, 3 volts and 9 volts, and 0s and 1s. So there's wires in your computer that if you measure the voltage on them, they'll have those numbers. We called this 1.5, we'll just call it 3 volt. So what we're going to do is say 0 equals that 3 volt wire, 1 equals the 9 volt wire. Well, how do you use that to say something useful? What we could do is, let's say we just wanted to count, and I wanted to hook up wires in my room and touch one or the other battery to send you a signal, to send you a number. And let's say I just wanted to send the number 1. So I hook up the 9-volt battery for 3 seconds, and your voltmeter goes bananas, and you read 9 volts. Well, you know 9 volts. We're going to call that 1. So you write down on your piece of paper a 1. And then, so I'm on my cell phone with you, and I say, okay, ready, measure the wires. I'm gonna put my number on the wires, and you measure, and you get 9 volts. So you get a 1. So you write down a 1. And I call you back, and I say, okay, let's do it again. You measure. I'll put the battery on. So I hook up the battery. This time I hook up the AA. You measure 3 volts on your voltmeter, and you know that that's equal to 0. So now you've written on your paper 1, 0. Now let's say, okay, I tell you I'm going to count. I'm going to change the battery every 1 second. I'm going to change to another battery. And you write down the voltage that comes. So on the first second, you write down 3 volts. On the second, you write down, you're watching your voltmeter, and it's bouncing between 3 and 9 volts. And you read 3 volts and 9 volts and 9 volts and 3 volts, etc. And you write down 0, 1, 1, 1, 0. And so I'm going to stop here because I have to think about what I'm doing.